Imagine if a minute felt like an hour, or if a day could stretch into a year. This isn't just a fantasy, but a fundamental aspect of our universe known as time dilation. When we think of time, we often perceive it as a steady, unchanging force, ticking away in the background of our lives. But in reality, time is a fluid and dynamic dimension, a stage on which events unravel in sequential order. Interestingly, time isn't a constant, fixed entity. It can be influenced, stretched, and compressed by various factors. One of these factors is the force of gravity, which can cause time to slow down or speed up, a phenomenon we call time dilation. This lays the foundation for some truly mind-bending concepts such as gravitational time dilation. So when we talk about time, we're not referring to a fixed constant, but a variable that can be influenced by the forces in our universe. One of the key ways time can be influenced is through something known as gravitational time dilation. This intriguing principle stems from Albert Einstein's theory of general relativity, a groundbreaking concept that revolutionized our understanding of space and time. Gravitational time dilation suggests that time isn't a fixed entity, but rather, it's a variable that can be altered by gravitational fields. Essentially, the strength of the gravitational field can influence how quickly or slowly time passes. Now, how does this work? Imagine the universe as a fabric, a canvas of space-time. Massive objects like planets or black holes are like heavy balls placed on this canvas. They create a dent, warping the fabric around them. This warping of space-time is what causes gravitational time dilation. In areas of strong gravitational fields, such as near a black hole or a large planet, time actually moves more slowly than it does in weaker gravitational fields. If you were to place a clock near a massive object, you'd notice it ticks at a slower pace compared to a clock in a weaker gravitational field. Yet from the perspective of the clock near the massive object, everything would seem normal. Its slower tick rate would appear to be the standard pace. This difference in the passage of time isn't just a theoretical concept, it's an observable reality. GPS satellites orbiting the Earth, for instance, have to adjust for the effect of gravitational time dilation. If they didn't, their timekeeping would gradually drift, eventually leading to inaccurate positioning data. Gravitational time dilation is a fascinating aspect of our universe, one that challenges our everyday perception of time. It reminds us that time isn't as rigid or predictable as it may seem. So the stronger the gravitational pull, the slower time appears to move. It's a mind-bending concept, but it's also a fundamental aspect of how our universe operates. But it's not just an interesting theory. Gravitational time dilation has practical implications, particularly in the field of space travel. During long-duration missions or travel near massive celestial bodies, this phenomenon becomes particularly important. Imagine a spacecraft hurtling through space at high speeds or skirting the edge of a black hole. The time aboard that ship would pass slower compared to a stationary observer in a weaker gravitational field. A fascinating example of this in action is our global positioning system. The clocks on GPS satellites orbiting Earth must account for both their high velocity and the weaker gravitational field. If they didn't, their timekeeping would quickly become inaccurate, throwing off the precision we rely on daily. So astronauts aren't just pioneers of space, but also of time. In a way, astronauts are time travelers, experiencing time at a different rate to those of us on Earth. But what about the kind of time travel we see in science fiction, where characters can travel backwards or forwards in time at will? Well, gravitational time dilation does allow for different rates of time passage, but it doesn't provide a practical means for hopping back to the dinosaur era or zipping forward to a future millennia away. Time, as we understand it, flows in one direction, from the past to the present and into the future. Gravitational time dilation merely alters the pace of that flow, not its direction. So the idea of jumping around in time, as appealing as it may be, remains a staple of fiction rather than fact. Speculative theories do exist, involving concepts such as wormholes or unimaginably advanced technology. These ideas tantalize us with the prospect of true time travel, but remain unproven and, for now, purely in the realm of speculation. So while we're not quite ready to hop into a time machine, understanding gravitational time dilation brings us one step closer to understanding the mysteries of our universe.